Good afternoon, everybody. It is my pleasure to be here to introduce Professor Tim Green, an outstanding academic at Imperial College and a very dear colleague of mine for the last 3 years in the Energy Futures Lab, in the keynote lecture that we have in our festival this year to talk about creating transitions in energy. Tim has made huge contributions in the activities of the Energy Futures Lab, and we very much look forward to his presentation and the Q&A that will follow. Thank you, Tim.
Thank you, Anna. Okay, indeed. Thank you, Anna, for the very kind introduction and warm words. Somehow, it has been 8 years since I was invited to become a director of the Energy Futures Lab. A lot has changed in that time. A lot has changed at Imperial. A lot has changed within the research domain in energy, in government policy, in public attitudes and perceptions of climate change. And it all seems to have happened really quite rapidly. So I know it's been 8 years I've been in this role, but sometimes I find it a bit hard to believe that that's really true. But as I approach the end of my term as a director of the Energy Futures Lab, I thought it might be useful and interesting to reflect a bit on what I've observed has changed and what the future holds, both for Energy Futures Lab and for some of my own research. So, when I became director, I had an opportunity to give a sort of inaugural lecture, which I did a few months after starting, and I gave it the title Being Smart with Energy, which was meant to convey two things, really. The one was, how does Imperial College and Energy Futures Lab be smart with energy? And we know that all of the big challenges facing energy are really interdisciplinary challenges. And we have to find ways to mobilize our resources and our talents on the campus to come together to answer those. So how do we be smart about addressing the big issues, but also how are we going to use the smart technologies? I think now we might call them digital technologies, but back then we were calling them smart technologies. And what roles would they play within the energy system? I was naturally a bit anxious about giving the talk. I never quite get over being anxious about giving talks, and my son must have picked up on that. He was 6 at the time, and he gave me this lovely homemade good luck card, which was charming. He thought I'd be talking to about 6 people around a table, not to 200 people in the Claw Lecture Theatre. Actually, and the reason for bringing that up is really because now he's 14, I can see the change that's in him and how prevalent concern about climate change and climate change mitigation and extreme weather events is more broadly. Although his school has very strong messaging about not joining climate strikes, he does at least bring in handfuls of green ribbons and hands them out to his classmates and encourages them to pay attention to climate change. As I said, one of the things that I talked about in that lecture back at the beginning was the smart technology. So there was a lot of conversations around smart buildings, smart grids, smart meters, smart cities. It wasn't entirely clear, I think, what all of that was actually going to amount to and how we were going to use it. But at least part of it seemed to be about using technology to mediate the way people wanted to interact with the energy system. So to build cyber-physical systems that meant that people could make choices and express their behaviors, and something else would be looking at how to optimize the energy use in the home. And that was going to be really important because as we stand down fossil fuel generation and rely more on renewables, we're losing the flexibility on the supply side. We can't just turn up a generator by burning more fuel. And to do supply-demand matching, we have to make more reliance on flexibility on the demand side, mediated by technology, but resting on the fact that we have some inherent flexibility within the way we charge electric vehicles or run our heat pumps. Behind the scenes, there's also a lot of smart technology going into power grids, in particular in the way we control and optimize those grids. But as I said, the second part of the smart was about being smart about how we interact with people. So smart in terms of the technologies that I've just, oops, my apologies, I wanted to get the laser printed up. But also engaging with people more generally in terms of, here an example of a community energy group in the village where I live, but not just those groups who have positive things to say about energy, but those who find themselves with large infrastructure, perhaps in their neighbourhood, and feeling hard done by because the benefits are arising somewhere else. So it's infrastructure in their area for benefits elsewhere. And we have to acknowledge the difficulties there and tackle those. I also thought about the engineering heroes that I looked up to. You might recognize Brunel's picture up on the top left there. You may or might not recognize the other person, Sebastian de Ferrante, and I want to come back and mention him again a bit later. But it's also about the people in the teams we work in, the research teams we build. But I think for Energy Futures Lab, it's much more about how we bring people together across the campus and have those conversations about what it is we can do together when we recognize the strengths and the interactions in the disciplines we represent. One of the things I talked about was just how challenging decarbonisation was going to be, and the way I did that was to reflect on the care identity. So you see it expressed there on the right-hand side. It says that total emissions from an energy system you could express as the number of people in the world multiplied by the GDP per person, multiplied by the energy per unit GDP, and the emissions per unit energy. And that brings you to a realization things are quite tough, because by 2050 we'll probably have 30% more people on the planet. GDP will have grown by maybe 2% or so a year over that period. We might be optimistic about energy intensity in industry and generally in our economy improving, but very easily you could find yourselves with much higher emissions, 70% higher emissions in the example I used. And if you want to drive it down, if you assume you could reduce energy intensity of GDP down to 40% of present values and carbon intensity of energy down to 40% of present values, you only end up halving emissions. And that's nowhere near enough back then. And now when we frame it in terms of a net zero ambition, it's very clearly not anywhere near enough. And there's only one term in that identity that you can drive to zero, and that's the carbon intensity of energy. So that's the goal. But it's not the only goal, because we have to realize emissions from energy are not the only emissions, and emissions of CO2 are not the only thing to concern ourselves with. But I think that reframing of the policy debate around net zero rather than low carbon has been really impactful. So if you compare thinking around a sort of 8% reduction with a net zero, I categorized it like this. I think in terms of energy efficiency, in a low carbon world, a lot of people are banking on energy efficiency helping more sectors fit within that remaining 20% that doesn't decarbonize. And the hard to electrify sectors such as aviation and shipping and heavy goods transport and some parts of industry all think they're going to fit in that last 20%. And the reframing around net zero really said everybody has to play a role here. And I think it's been particularly marked in recent weeks on aviation, with a lot of talk of electric aviation and synthetic aviation fuels. That industry has had to change because of the reframing. Carbon capture, I think, has changed. We heard a bit about that in the first session today. At 5 or 10% non-capture rate from CCS, you can tolerate that in a low carbon world. You can't in a net zero world. You have to drive non-capture rates down to very small, and you still have to pair it with some negative emissions technology. And when we look at hydrogen, which is very important for sort of local emissions, you've got to think about where the hydrogen comes from in a low carbon world. Steam methane reforming and CCS is what we sometimes call blue hydrogen, seems an adequate way forward. But in net zero, it's got to be zero emissions hydrogen. And if we go closer to my own field and think about electricity, short-term balancing within electricity systems. In a low zero world, we could run unabated gas for a few hours a year to get us through particular problems. And CCS would help us through longer periods of low wind output, or sometimes called a Dunkelflatter. But in the net zero world, we're going to have to make much more reliance on energy storage and probably also zero carbon fuels as a way of getting us through long wind lulls. So I think the net zero framing has really changed our outlook. With the team at Energy Futures Lab, we reflect on things like that, and we think about our strategy for the energy researchers on the college to try and help our colleagues. We do that by thinking about the strengths and the weaknesses, the opportunities and the threats, a traditional approach. I mean, where we find a strength with a continuing opportunity, it's a very simple decision. You just carry on doing it. And I think in these 4 areas, Imperial's long had a strength, and we continue to work in all of those 4 areas. And as Energy Futures Lab, we continue to support that and help people bid for new projects and build relationships with industrial partners and so forth. What's perhaps more interesting is those areas where we have a potential strength or an unrealized strength, and there does seem to be an emerging opportunity. And in the last time we refreshed our strategy in sort of 2016 or so, these 6 things popped up. I'm going to spend a little bit of time on each of those and just reflect on where we got to. And before I do that, I'm going to have a shout out for Tanveer Hussain, who is an academic at Nottingham and someone I follow on Twitter. And he captured very well something that I strongly believe, that we need to be a bit careful when we talk about our successes, particularly as established researchers. As for early career researchers who are sat there thinking, well, I've tried a few things and several of them have failed, I think we have to be a bit more clear that we all have a long list of things that we attempted, which we thought were terrific, that didn't come to success. And Tanveer expresses it like this with this iceberg view, so visible and above the waterline, he's got the things that he's succeeded in, and he's got some nice research grants there. And below the waterline that you never see are the papers and the grants and things that failed to get forward. So I'm going to try to do an honest reflection here, but I am going to start with something that I think was very successful, which was our recognition of the importance of energy system integration. So recognizing that electricity and heating and cooling and transport use of energy and industrial use of energy are systems that increasingly interact with each other in a wider energy system, and that if you want to operate and plan such a system to be cost effective and reliable and so forth, you have to apply systems engineering principles and you have to do whole system modeling. Now, those are things that Imperial does well, and it has depth of expertise in all of the different domains. And we brought together a team at Imperial and bid for a single institution program grant, and that was successful. It works across 7 departments and brings together a lot of researchers, and it's something I think we're quite proud of. It wasn't always an easy path. There were some roadblocks along the way we had to clear, but we got the Research Council money and a nice set of industrial partners co-funding. Another thing that's been successful was the recognition that as electricity sort of was at the front of the charge to decarbonize, as that was successful, attention would turn elsewhere, particularly to building heating and our use of gas. And we mobilized on the campus to get people to discuss what we know about building heating and how we could approach that in future in terms of heat pump technologies and built environment and all sorts of things. And once we had those ideas clear, we talked to people in BEIS and Committee on Climate Change and elsewhere to road test our ideas, so that when the calls came out from the research councils, we were very well positioned, and we've been successful across the campus in securing individual research grants. And there's a similar story around industrial decarbonisation. Imperial has a lot of individual strengths in process industries and fuels and so forth. And to have gained a strong role within the Industrial Decarbonisation and Innovation Centre, IDRIC, is very important. And I pay particular tribute to my co-director, Anna Corey, who led that activity. And it's great that we have such a strong role there and have secured individual research projects within that centre. Say a little bit about offshore renewables, where I think the picture is a little bit more mixed. So offshore renewables, hugely important for the UK. We built 10 gigawatt of wind. We're going to build a lot more in coming years. This is Rampion offshore wind farm just south of Brighton, where we sometimes take our MSc class or PhD students for a boat trip, which is rather lovely. Across the campus, we've got a lot of individual strengths in aeronautical engineering, blade design and so forth, and wind tunnel facilities for testing it, in structures and foundations, and particularly offshore structures and their testing in wave tanks and civil engineering, in grid interfaces and grid control around wind, lots of strength. But I think Imperial had always fallen short of putting that together in a way that really made big impact across all of those disciplines. And we have tried, and we've had some success. I think we've had some recent EPSC successes. We've got a good relationship being built now with SSE and Equinor, more recently with Met Office on multi-scale modelling and wind wave interactions. But it very much feels like unfinished business. We have a lot more to do before I think Imperial has really recognised it in a leader in offshore renewables. Also, perhaps unfinished business is our thinking around energy in the developing world context for low and middle income countries. Most of our work on the campus is focused towards developing world. There's a small group of dedicated people who look particularly at energy in the developing world, but I think we've got to do much better to broaden that. And I think Imperial faces two difficulties. The one is, to be successful in this area, you need really good partnerships. You've got to be credible about how you're going to get impact in relevant countries from the research. That means building those partnerships. And the other thing is that many of the difficulties faced are socio-political in nature. And we have people who can deal with that, but most of us on the campus are scientists and engineers, and it's really quite hard, sat in London, to think about what really are the science and engineering challenges that you need to unlock to improve energy access in low-income countries. So we've sought out partners. These are pictures of workshops we ran in Nairobi with Strathmore University and various other partners. And I think we now have some nice partnerships that are credible for impact, and we have some better ideas about what challenges we can address across the campus. Our timing was unfortunate. We got ready just at the point the government turned the tap off on funding in this area, and we're sort of waiting patiently for the government to open that tap back up again. We have a very successful MSc program, something we're very proud of, that it builds a cohort each year of 50 or so multidisciplinary engineers and scientists and business leaders. And we've always wanted to do something as broad and as strong a cohort in the PhD studentship space. And we've tried with partners in Mexico and China and Brazil. We've tried with Leverhulme Trust. And this is one where we still haven't really nailed this. It's quite hard to find the partner who will want to do that with us and has the deep enough pockets. We've had some successes across the campus on centres for doctoral training within energy, but they tend to be rather narrowly drawn, and we haven't done the wide piece yet. So perhaps another piece of work in progress. And I've wrapped this section up with something which we have been successful on, which is our policy briefing papers. We've always had people here at Imperial who like to take evidence from science and engineering research and take it to policymakers in governments and also in industry. But we've often been doing that as part of other collaborations, Supergen Consortia or UK Energy Research Centre, and very little was going out as Imperial's policy outputs, and we weren't getting the recognition that perhaps we deserve. And so with the help of the Vice Provost, we identified funding that would let us publish such papers under our own banner, and we've got 8 of them published. Together, they've got about 5,000 downloads off our website. We will easily get 200 people along to a launch event. And perhaps more important than any of that is that these are picked up and quoted by Committee on Climate Change, on BEIS, the All-Party Parliamentary Group on Energy. And I think we are now getting recognised as a place to go for policy advice, particularly where it builds on science and engineering advice. So that's a reflection on how the strategy in the most recent period has played out. Some of you will know, because we recently launched it, we've been refreshing our strategy. How did we do that? Well, we organise and we think about the research on the campus under 6 themes. It was originally 5, and as part of this most recent process, we started a new theme on materials for energy. So we have conversations with all the friends across the campus. And so we would normally do that in workshops. It's been a little bit more difficult recently, so much of that has had to go online. Nonetheless, we've had those conversations and got specific ideas under each of those headings. But out of that have come some broader thinking about the things that are driving research. So one of them I've mentioned, which was the net zero reframing and how that changes our research objectives and imperatives. Another has really been the moving on of the debate on climate change and sustainability more generally, to put energy research in a broader definition of sustainability, and to continue to think about, even though arguably it's been on a slow burn, the digitalization of energy. I won't say any more about net zero because I think I covered that, but on sustainability, it means thinking much more about the manufacturing process for the technologies and the infrastructure that we build. What are the sources of the raw materials and what's the environmental impact there? Are we designing for refurbishment or recycling or materials recovery at end of life for some of those technologies? So it's a much wider picture of how energy research is defined. And the same will be true on other environmental concerns such as air quality. And I think the energy sector has been a little bit complacent historically, thinking that as we clean up our use of fossil fuels, we'll drive down particulate emissions and SOx and NOx and so forth, and that will bring air quality improvements. And as we get rid of tailpipe emissions from vehicles by using batteries or hydrogen or something, that will clear up local air quality. So first we have to recognize on vehicles, a lot of the air quality and particulate damage is from tire degradation, and there are wider aspects of environmental impact that we need to address. So I think that's an interesting reframing for researchers on the campus, and it well aligns with broader strategy at Imperial. On digitalization, I think we have brought inside of energy research some of the consumer behavior piece by thinking about ways in which we can use machine learning to characterize choice and behavior by people. Some of the technologies I mentioned earlier, so the fancy home thermostats and so forth, has progressed maybe less quickly than we might have imagined it would. So we're not really seeing the impacts of the digitalization of energy in the consumer field, but we still believe it's coming. In the industrial field, and recognized by our friends in Hitachi and Hitachi ABB, digitalization in technology side is certainly there. And it's interesting that our policy briefing paper on digitalization of energy that kind of set out what the opportunities were across the energy field and across the machine learning and AI field is our most popular and most downloaded briefing paper. So that strategy launch, we launched it last week. It's available for download. It's got much more detail in it than I can do in a few slides, breaking it down into those 6 thematic areas. I wanted to spend a little bit of time reflecting on how research is changing in my own domain and where that's going. So what are the electrical engineering challenges in a net zero world? So we covered some of that in a briefing or white paper from the Ilios Project. We made certain assumptions on the costs and performances of a range of energy technologies, and then you run a fancy optimizer looking at what is the electricity system you build for a 2035 system in Great Britain. And there are lots of different answers depending on exactly how you frame the question and the scenarios you choose, but there are some big conclusions alongside the detail, one of which is we will need to build an enormous amount of offshore wind, something like 100 gigawatt, which compares with 10 gigawatt today. That's a fantastically challenging build rate in the next 14 years. We also build a lot of storage, particularly to meet peak demand in a reliable fashion. But we also need storage for energy purposes to get us through both short run and long run lulls in wind and other renewables. Beneath that are a couple of more technological changes, which I think are interesting. In those generation mixes on the right-hand side, there's almost no conventional generation. There's a small amounts of nuclear, which are electromagnetic generators, and almost everything else, the storage, the wind, the solar, has an electronic interface to the grid. So let me just unpick all of that a bit. So traditional generators, a big spinning electromagnet spinning in the middle of a steel stator, which carries the main power windings. That defines the main characteristics of the system, the rotational speed of that electromagnet, sets the AC frequency. There's a set of inherent sort of feedback loops there that mean when you connect a new generator to the system, it locks in and it runs in step with all the other generators. They rise and fall in speed together as a set. And the dynamics of that are relatively slow, the mechanical system, and the dynamics even with the electrical system is faster, but not terrifically fast. Just going to take a little box out to come back to Sebastian de Ferrante. In the late 1880s, at the age of 24, he was appointed as the chief engineer of the London Electricity Supply Corporation. And at a time when Westinghouse and Edison in the US were arguing fiercely over whether a system should be AC or DC when you electrify a city, Ferrante set out with remarkable clarity why it should go one way, not the other. And his logic was, he was tasked with bringing electric light to the galleries and fancy residences of the West End of London. He realised he couldn't build a power station in the West End, he couldn't afford to buy the land, and he couldn't get the coal there even if he could. He built his power station in Deptford. If he had to get the electricity from Deptford to the West End, he couldn't do it at low voltage, he'd have to do it at high voltage. If he had to do it at high voltage, it was going to have to be AC. So it was going to have to use transformers. If it was going to use transformers, it had to be AC. Done. I think he was remarkable for the clarity with which he approached that problem. So off he went and he built his AC generators in Deptford. And I think if you asked him back today and said, take a look at our generators of today, he'd have two reactions. On a detailed level, he said, your use of materials and your manufacturing processes and tolerances are remarkable. But on the big picture, nothing's changed. Your generators look just the same as my generators. We have spent 100 and something years building an electricity system around a technology of these traditional machines that hasn't changed. But it is changing, and that's my point. The solar panels are DC. We have to turn the electricity into AC with an inverter. The wind turbines have an AC generator up in the nacelle, but it doesn't generate at 50 hertz. It varies its frequency as the wind speed changes, and you need an electronic interface. And the important thing here is that electronic interface, its characteristics rely very little on the physics. The semiconductors and the components define some of it, but it's largely defined by its control structure, which really means it's software-defined behaviors. It'll do what you tell it. That's its charm. You can design it to do lots of things, but it only does what you tell it. And if you don't give it a behavior to a particular perturbation, it won't help. So the contrast is telling between the traditional machines defined well-known differential equations with inertias and electrical reactances and things that you can model quite easily and are well-known. These are open models shared across the industry, relatively slow dynamics, whereas the inverters are proprietary. Each manufacturer does them different. You can't tell exactly how because they're opaque. They don't reveal full models, and the dynamics are much more complex and interact. And it's challenging, and various system operators, grid operators, if you like, around the world have realized how much the system underneath them is changing as the equipment people connect is changing. These six have come together in something called the Global Power System Transformation Consortium. And I've been working on that with friends over the last year and a half to pick apart the way in which we ensure our system is reliable and cost effective. What services do we get from the connected equipment that keep the system stable and secure? How do we synchronize devices? How do we control frequency? How do we damp oscillatory modes and so forth? And we have to go back and we have to redefine all of those in technology neutral terms rather than the way we've traditionally defined them, and then recognize the limitations and the features of the new technologies, that our semiconductor devices have very limited emergency rating. You can't get extra power through them for half an hour in an emergency. They just have a strict limit. If they're connected to a renewable resource, you can't suddenly turn the power up. You're going to have to look to a battery or something to get short-term additional power. And it redefines the way in which we build the grid, I think. At the moment, the inverters that exist are getting a free ride. We're still relying on the existing traditional generators to control the system, whereas the inverters sources just produce energy. But as we stand down our traditional generators, we have to get our services from those new sources. And I think if we do that in an unchanged way, we will build lots of additional cost into the way we have to build our inverters. So the overall cost of the system will get quite high. We will end up on this right-hand side of the diagram with high-cost inverters and a poor system. If we say, well, let's not redesign the inverters to fit the grid, let's redefine the grid to fit the way inverters operate, we end up across the other side. We build lots of cost into the grid. And we need a well-managed, well-thought-out, mediated solution in the middle there that minimizes cost. And if I could draw those cost curves, we could find the minimum of that curve. The trouble is we can't yet draw those curves. We don't understand the situation well enough. Okay. A couple more slides and I'll wrap up. I want to illustrate one more thing that I find fascinating and I want to spend some time on. And to illustrate it, I'm going to go back to an event 2 years ago, August 2019. There was a blackout in the UK that took about 1 million consumers in Great Britain off supply for half an hour or so. The bad news is about half the problem was a wind farm. The less well publicized good news, about half the solution was a set of batteries. So new technologies sort of were part of the problem and part of the solution. What happened? There was a lightning strike to part of the grid just outside St. Neots. That sounds dramatic. It isn't. You get 800 or 900 of those a year. It's completely routine. Normally, circuit breakers open. That extinguishes the arc caused by the lightning. You only need to do that for about 50 milliseconds, reclose the circuit breakers, and everything carries on pretty much undisturbed. This time we were unlucky. 2 generators disconnected in response to that single lightning strike. That's highly unusual for one to do that, and 2 is exceptional. We don't carry enough reserve, the batteries, to lose 2 big power stations at the same time. But the question here is, why did the wind farm disconnect? The wind farm was more than 100 miles away. At the wind farm site, the voltages dipped by about 10%, which is really not very dramatic. But what happened was the wind farm tried to improve the system voltage by injecting some reactive power, and it exposed the fact that it had an unstable oscillatory mode. You can see the oscillation develop there, and then the supervisory system cut in and shut the wind farm down. So the question is, why did we not know there was a poorly damped or unstable oscillatory mode in the system? And there are lots of reasons why that's becoming increasingly difficult to do. The system orders increasing. We've now got thousands, arguably hundreds of thousands of wind turbines and batteries and so forth, rather than 200 generators. The dynamics of these systems are much more closely coupled. We used to be able to partition and separate the system out and address different dynamic properties in separate analyses. And we had full and open models of the system, and now we have these black box models, limited disclosure by the manufacturers, which prevent us doing the sort of root cause analysis we've always done, which is to take the state space model, get the eigenvectors, and from that you can work out how much each state of the system participates in an oscillatory mode. And if it doesn't look well damped enough, it also helps you understand how you retune the system or redesign the system to make it stable again. So how do we ensure stability when we've got lots and lots of black box models? Well, part of it is to open those models up a bit more and make them grey box, and the other is to go after data-driven rather than physics-based models. So you can do this in data-driven form by injecting perturbations into the network at various nodes, and you inject a bit of current and you see how the voltage responds, and you sweep that across the frequency, and at the different nodes you can identify various oscillatory modes. You can either do that analytically or you can do it as a real experiment. We've done some of that on our models of the New England test system, which is one of the classic test systems in this field. So these big complicated electrical network, you do test injections, you sweep the frequency, and you gather all of these various modes. And there's a mode here at 5.6 hertz. I can plot that on the eigen diagram on the right-hand side. It's got quite a significant negative real part, which means it's well damped, so that's fine. The next mode, mode 2, is higher frequency, and it's less well damped. And if I wanted to damp that, I've then got to go and retune something. So far, that's entirely standard. What we've been able to do is then pick apart that with some limited information of what's inside some of those black boxes, combined with this frequency sweep analysis to work out how each of the parameters of the system affects the damping and the frequency of those modes. And that gives us a way to then spot unstable situations, but more importantly, retune them. So that's been a nice piece of work recently completed. The challenge is this is done for just small perturbations around an operating point on linearized models. We've now got to go on and tackle nonlinear models, and we've got to look for all sorts of other features of the system, such as the frequency stability and the synchronization stability. So that's where I'm going next. I'm going to spend a bit of time back at the research phase, thinking more deeply about some of these. Okay, I'm going to wrap up now. I need to say thank you to a number of people. I suppose first of that list would be Jeff McGee, who was Dean of Engineering at the time, who invited me to be a director in the Energy Futures Lab. And then the Vice Provost, Nick Jennings, and now Mary Ryan, who are the three people who've been the people we've turned to support Energy Futures Lab and the other global institutes, and to give us the funding for the things that we set out to do. I should also thank Nigel Brandon. He was the first director of the Energy Futures Lab. He set it up very well, and he handed over something that was in very good condition to me. I've worked with various deputy directors and directors of education and policy, so Anthony Kusanak, Johannes Spinnaken, Rob Gross, Graham Hughes, Faye Tang, most recently Anna Corey, who for the last 3 years has been a co-director with me, and we've shared responsibility for this. And I know Anna has brought great enthusiasm to that role and many talents, and will take this forward in a very positive way with the new co-director, Peter Childs. We've got a great team in the office. Some of you will have met. So Vicky, Nick, Gavin, Connor, Alex, Amy, and Aidan, who are a great team of people. Alongside them, our advisory board, 8 super people in industry who give up a big piece of time to help us plan our strategy and other things. Our strategy board, which are heads of department and vice deans for research. Also, all of the researchers on the campus, but also particularly the theme leads and theme champions who help us in Energy Futures Lab. And particularly, because it's been a big part of my time of Energy Futures Lab, the investigators, the PhD students, the RAs within the IDLES program, and 2 people who help with the IDLES program, so Catherine as program manager and Phil, who looks after the Hitachi demonstrator. I've also got to thank my own research group and my friends in electrical and electronic engineering, because I've been 50% away from here, 50% in Energy Futures Lab, and they've had to sort of stick with me as I've had half of my attention focused outside of their own research. So if I've forgotten anyone specifically I should have included in that list of thank yous, then I apologize. It is a broad thank you to a lot of people, and thank you in particular for your attention this afternoon. Thanks.
Excellent. Thank you very much, Tim, for a wonderful presentation. We enjoyed the technical discussion and the discussion of your own work, as well as your reflection in the period that you have been at EFL, and also seeing the developments at the college. There are a lot of questions in the chat, and there might be some questions in the room. So before we start with the questions from the online, I would like to give the audience who is present and here and honoring us with their support to raise their hand and give us any questions.
Yeah. So you have highlighted that we need a drastic change in the sources of energy we use. Phasing out of fossil fuel in 2050 is a necessity if we want to meet our net zero targets. Yet, do you believe that the money is flowing at the right place? Do we seem to invest drastically in CCS, hydrogen, reducing the fossil fuel emissions? But are we investing enough in effective and efficient solutions like energy storage, renewables, or even nuclear, for instance?
Gosh, yes. I suppose you could be optimistic and pessimistic, maybe even at the same time. We are building, across the world, building renewables at a fantastic rate. It's still got to step up. In the UK, we've got to increase our wind by a factor of 10, which is a huge investment. But that's now an investable proposition. You don't have to subsidise wind. It's a well-known revenue stream. The business case is well made. I think that's becoming true of storage within electricity networks. There's more than 1 gigawatt of storage in the UK. The business case is there. The costs are coming down. And it is a feature, isn't it, of certainly these technologies that you can do learning by doing, solar, wind, batteries, get cheaper as you build more of them, as you get better at building them, and then the business case strengthens. It's such a nice positive feedback loop. There's lots of other things, investment in charging infrastructure for electric vehicles, that seems to be moving. Nuclear, we could have a long debate on the financing of nuclear, and it looks like the UK government will change its mind about how it finances nuclear and whether the next stage will be any more affordable than the previous stage. I'm not well qualified to say, but I don't think we should underestimate the scale of the change and the continuing need to subsidise some of the technologies that aren't yet at a maturity where they just compete on their own terms with fossil fuel. So we still need to subsidise some, and it's a big the amount is huge. So that's got to be government. Yeah.
So you mentioned a little bit the energy materials as a new strategic point.
Yeah.
Can you go into any work that's already ongoing in that direction, or?
I'm not the best placed person. It's not strictly my field, but it's always interesting how often cost reduction and efficiency improvement or a new technology relies on an innovation in materials. So I know that from my own work, and I recognise that. I think some of the most startling work now is in synthetic fuels, the catalyst systems, the electrocatalysts, and to do electrolysis, high temperature, high efficiency electrolysis, solar routes to hydrogen, and then uprating of hydrogen to more energy dense molecules. A lot of work around the catalyst field, but there's still needs for better. We need better electrical insulators, better thermal insulators, all sorts of materials challenges which are ongoing on the campus. After that, I would normally turn to colleagues and say, give me the detail. Although I sit here as a director and so do Anna, I mean, there's no way one person will cover the whole domain.
Is any of the ongoing research also into plant research into the actual supply chains behind solar PV and wind?
Yeah, certainly, and Anna's own work as well as others on the campus in terms of what are the minerals that you're after. Increasing emphasis on nature abundant materials rather than exotic materials, and of the energy and other wider impacts of the mining process and the materials recovery. So I think my point is, although that might not always have been our focus as energy researchers, it is increasingly, and our strategy is that it has to be. Yeah. So one over here.
Yeah, I guess you kind of maybe sort of answered it. I was going to ask about how much of the research will be into the kind of unintended consequences of all of the deployment of technology. I mean, you talk about a 10-fold increase in wind offshore, that's an immense amount of material, and transport and installation carbon costs essentially associated with all that. So, yeah.
Yeah. So I think on the wind piece, I mean, we probably know a lot about the supply chain and the logistics of deploying it, and we could probably do pretty good estimates of the environmental impact. And there's a lot of work done on the impact on the marine environment. So that's probably one example where you can do the sums. I think your question started with unintended, can we model the unintended consequences, to which the answer is, well, we don't know what we don't know. It's the famous sort of Donald Rumsfeld quote, isn't it? I think we have to be alert to the fact that, as technology researchers, we can get sometimes a bit carried away, and we have to think more. That is that reframing. What are the potential consequences of what we're doing? We need to decrease the number of unintended consequences. We have to know better what the consequences are of the things we seek to deploy. We've learned too many hard lessons over the history of humankind not to want to do that.
Can I please interject then a question that came from our audience? And this is a little bit closer to your area of research and talking about the renewables. So one of our colleagues is saying that it is obvious that we are still learning about the operation of renewable energy systems. and in this case we are talking about wind. How optimistic are we that they will be ready and we will be able to replace well-known systems that are using fossil fuels? And a related question about the technical challenges, and how much time do we think it might take to resolve these technical challenges?
Oh, right. Okay. Well, I'll take the second one first, and remind me if I drop the first one. The second one, how much time will it take? I think we need to invert that. We know how much time we can be allowed. So we have to decarbonize, fully decarbonize the electricity system in this country by 2035, in order that you can then fold in other sectors of the economy into electricity in a decarbonized fashion. If we're not on that trajectory, we don't hit 2050 as a decarbonized economy. So electricity is at the forefront, and we have 14 years to fully decarbonize it. So you have to work backwards from there. So, that you can't have a succession of 3-year research projects. By the time you've got 4 of them together, you've pretty much run out of time. Am I optimistic we can do that? Yes, as one of my colleagues says, people have done tougher things. They've put people on the moon, they've landed probes on asteroids whizzing past and so forth, all sorts of things. When you mobilize, you can do it, and we have to mobilize and we have to do it. I think we say some of the ways forward, as an engineering community in particular, we should rise to that challenge. It should be exactly what we enjoy doing. There's something that is quite technically difficult to do and absolutely needs to be done. That's us, isn't it? That's what we went into engineering to tackle. In my head, there are several things we don't know how to do, and we will be having to do them as business as usual in 2035, but we will get there. We will do that.
Okay, so a related question from another attendee. So amongst the different technologies that can support the future flexibility requirements, we have batteries, DSR, interconnectors and supergrids, hydrogen, synchronous condensers. Can you bet can you choose which might be the most promising?
Oh, the most well, yeah. The standard answer is you need all of them, because partly for the unintended consequences, you want a portfolio so that you've got a broad set of ways of responding to difficulties. I was in a meeting a while ago where it was a bit sort of upside down. The engineers were saying, look, demand side response is actually quite cheap. You're just asking people not consuming this period and consuming that period instead. It's cheap to do, so that's what you should do. And the social scientists were there saying, you should build batteries. Have you any idea how difficult it is to affect behavior change? So the social scientists wanted a technology solution, and the engineers wanted a behavioral change solution. And I think it was both sides recognizing the difficulty in their own domain and seeking the solution in the other domain. So batteries and demand side response or behavior change will need to come together. It is quite unclear, I think, what the balance between them will be. And I think we have spent at least 10 years thinking demand side response is the big prize, and we're not there yet. We don't really even have any major, huge, big scale, at scale trials of that technology. And the other stuff, the more techie stuff, the international interconnectors and the various bits of kit, we know how to do that. So that might be something that we decide we want to build while we wait for some of the other stuff to come good.
Okay, wonderful. And if I may add on a question from Herve, who says that you have given us a small share of nuclear power estimated to be in use in 2035. Do we really need new power plants, or could we manage mainly with the wind turbines and the storage, do you think?
We could in GB build a system without nuclear, that's true, and there are plenty of countries that will choose that route. In 2035 we will have nuclear, because by then we will have Hinkley Point C and we'll still have Sizewell B. We may have Sizewell C. I've always been agnostic on nuclear, and it really comes down to cost and delivery timescales. I think, can we build stuff for 2035, and can we build it at a cost that makes sense? And in those studies that I alluded to, if you could get the cost down to £45 per megawatt hour, it's a levelized cost, then it was worth building more nuclear. But it still was not a big part of our system. So to be a big part of our system, nuclear would have to get an awful lot cheaper than it is today.
Mm-hmm. Wonderful. I have two more questions in the chat, if you can bear with me. Yeah. Well, so an anonymous who has got a lot of votes on his question, he's asking you, Tim, how will the UK energy mix is going to look in 2040, 2050, do you think? This is like staring at the
UK energy mix rather than electricity mix. Yeah, I don't have quite so much hard data to fall back on. Well, I mean, firstly, every nation of the world will come to a different solution just because it has different resources. Different nations have different fossil fuel resources. Different nations have different renewables resources. We're in windy Northwest Europe. That's going to be our mainstay. We will have some solar. We may get a bit of geothermal. We may yet exploit our marine resources better. So tidal flow turbines, tidal lagoons in the Severn Estuary. Those are some technologies that still need significant financial support. And that is our route to decarbonized fuels, presumably. For us, for domestic production of decarbonized fuels, it's going to need to come from electricity, which comes from wind. Will we be importing? We'll be trading electricity with our neighbours back and forth, depending on where it's windy and where it's sunny. But we will probably be trading low carbon fuels. And so it does look like the Gulf states and North Africa and some other domains will build large volumes of renewables and generate hydrogen and uprate that to ammonia or something similar for shipping. And we will have an international trade in low carbon fuels in the same way as we have an international trade in fossil fuel.
Wonderful. And that tells us that there will be no fossil fuels in our predictions.
We can't do it.
Absolutely. Thumbs up. I just want to make absolutely sure.
Bad.
Wonderful, wonderful. So the very last question here, which is like you have to tell us what is your favorite next research project. So if you were offered a carte blanche budget, well, where would you choose to put the money? But think substantial, yeah? We would trust you with a lot.
Yes. So there's possibly two answers. There's my answer, what would I want to do? And I know the answer to that because I've been thinking about a big ask to UK government on electricity transformation. I think we are in danger of arriving at 2035 with enough kit to have a fully decarbonised electricity system, but we cannot operate it reliably in the way that people expect. Freedom from power outages across the year. We can't arrive there and not know how to fully operate it, or have to overbuy batteries or overbuy other technologies and create a non-cost-effective system. So I think there are some really difficult technical challenges to operate a fully decarbonised system in a cost-effective and reliable fashion. So that's great university research, with the caveat that we've probably got 4 or 5 years to do that research, and then it absolutely has to start deploying and become business as usual in 2035. And that's not the way, honestly, we've all done research through our careers. We've had quite a lot of bites of that research cherry before it gets to deployment. We run out of time for that. And the second answer would be perhaps more broadly at Imperial. It's low carbon fuel. There are parts of our economy which will require high energy density fuels, aviation, shipping, maybe not so much density, but also fuels for industry. And although there's a lot of good work initiating, I don't think we've got the volume of work in that sector that we need. We need tens of millions of pounds to get done.
Thank you, Tim. Thank you. Thank you for a wonderful lecture. I can't see any critical questions anymore online. And I just wanted to say a few words, a little bit from my own personal point of view, as a colleague who came and joined you and actually met you for the first time about 3.5 years ago. So I must say that I have been extremely impressed by your commitment and your diligence and your enthusiasm to make sure that everything you do is at the highest quality standard. And that has been really obvious in everything that you have done in your publications, in your research track record. And while doing this, you have also been a very pleasant and polite and kind and generous colleague to work with, which I have been very lucky to experience and learn in the last 3 years. I'm very grateful to you for this.
Sorry.
I also know our team in the office appreciates you very much, and the colleagues outside have an excellent opinion of us because of you, and your ability to actually project the positive face of the college and an EDI, an equal, diverse, and inclusive activity that we have in the lab, that you inspire in your department, that you inspire in the college, which is also very commendable. So I am extremely lucky that you're going to continue to be at the college and you're still going to be in the same building, and I will be able to track you in the lobby and come up to your office and make sure that you continue to be our friend and good colleague. And we look forward to many more opportunities to continuing our joint research and being successful. And thank you very much for a wonderful lecture today. Thank you.
Thank you. Thank you, Anna. That was very kind, and I'm touched by what you said, and I know the high standards you set for yourself as well. So and how enthusiastic and engaged you are. So to hear you say that is very nice indeed. Thank you. And I absolutely am not disengaging from Energy Futures Lab. I'm just handing over to you and indeed to Peter to run the show. But I'm still an active part of Energy Futures Lab, I hope.
Yeah.
Great. And thank you everyone for being here today in the audience and for being online as well. Great. Great.